couple integrals involving trig functions, and in particular sines and cosines. So usually the way we're going to get them is sine raised to some power times cosine raised to some other power. And that's really problematic because we don't know how to integrate sines and cosine raised to different powers. So the way we mitigate that situation is by trying really, really hard to make it look like sine raised to some power times cosine dx. And this could be swapped, so it could be cosine raised to some power times sine, but I didn't want to write them both. So we try to make it either look like this or this. And again, there could be other variations. It could be 1 plus sine raised to some power, but the basics are we want to have this part. This is the important part that we must have. And it has to contrast with the function that's being raised to all the weird powers. So if you have 1 minus cosine to the 5th all raised to the 7th, this guy has to be sine, okay? So all we're really looking for is to separate them and have one of the functions be raised to the first power. That's it. It doesn't matter what the other function is doing. It could be doing any business it wants. As long as that's true, as long as we have the function raised to the first power times dx, and that's the only occurrence of that certain function, then we're good. Because the reason is we can take the other function and make that our u, and when we derive it and find du, pops out the other function. Okay? So let's go ahead and do an example here. We got sine to the 5th x times cosine to the 4th x dx. So first thing I'm going to do is really look at this and envision how it's going to look after I start messing with it. So I have cosine raised to the 4th and then sine raised to the 5th. If you've sort of noticed when dealing with trig functions, they usually happen in even powers. So whenever we have formulas and whatnot, they usually involve sines and cosines in even powers. That's just because of the way sines and cosines and trig functions in general are created, and they're related to each other. We really like them when they are in even powers. Okay? So if we have an example in which you have one sine or cosine have an odd power, you're in luck. That's the easiest example to do. Why? Because all you got to do is pluck off one of the signs and write it like this and say sine to the 4th x, cosine to the 4th x, and sine x dx. And then these two don't have to match. That's just a coincidence. But the important part is sine x dx. Why? Because it almost looks like what we have here, except we have the sine to the 4th x messing us up. Because otherwise, we would have just said cosine is my u, my du is sine x dx, done. But we can't because of the sine to the 4th x. So we somehow have to get rid of the sine to the 4th x and make it look like something in terms of cosine. We do that, we're done. So the way I'm going to do that is very simple. I'm going to use my handy-dandy Pythagorean theorem and say, okay, well, I know I can write, I know sine squared x. I can write that as 1 minus cosine squared x, but I don't know what sine to the 4th x is. But no problem, because I can write sine to the 4th x as sine squared x squared. It's like a little pet trick, okay? So, and then I'm going to write my sine squared as 1 minus cosine squared x. Okay? So, again, fairly simple, but very effective, because look what's going to happen now. Now I'm going to have 1 minus cosine squared x, cosine to the 4th x, sorry, this is all raised to the 2nd power, cosine to the 4th x, sine x dx. Now that looks really messy, but look what I can do. I can say I only have cosines raised to weird powers, so now I can just do my u sub. U is cosine x, and du is minus sine x dx. And now I can clean this up a whole lot. I can say 1 minus u squared all squared times u to the 4th times du. And you see how simple it is to do this guy? And yeah, I'm sorry, I forgot the minus for du. So it's very, very simple, And this is a very easy integral to do. You just distribute out the 1 minus u squared squared, and you just basically do the polynomial integral. So that's the case if we have an odd and an even. Very easy. Pluck off the odd and just go ahead and make this even. So if you have sine of the fifth, cosine of the fourth, pluck off one of the signs, put it out front, make the rest of the signs look like cosines, and there you go. You just need a u sub. So what if you have an even? Okay, so what if you have sine of the squared, or sine of the fourth, or sine of the sixth, or cosines? Well, that's a little different. It's still sort of the same idea, but a little different. Okay, this time we're going to use the double angle formula, and in particular the cosine one. Cosine 2x is cosine squared x minus sine squared x. That comes in 3 flavors, one involving only sines and one involving only cosines, but I usually just remember this one and then derive the other ones, just because I can't remember which goes with which one. So here, what I'm going to do is look at myself and say, okay, well, I don't know how to deal with sine of the fourth x, so I'm going to somehow try to make this look like something that I can deal with. I'm going to use my pet trick from here and make this look like sine squared x squared. Okay? Now, sine squared x, I know how to write in terms of something that's linear. Okay? Cosine 2x is linear, whereas cosine squared x and sine squared x, they're all quadratic terms, right? So what I'm going to do is I'm going to use this formula, except for the fact that it's going to give me a cosine squared, right? I'm trying to get rid of the sine squared, but if I just plug this in, I'm going to get sine squared x is equal to cosine 2x minus cosine squared x, and I don't want that. I don't want the cosine squared x term. So what I'm going to do is use the Pythagorean theorem to get rid of the cosine squared x. I'm going to write it as cosine 2x is equal to not cosine squared x, but 1 minus sine squared x, and then minus sine squared x. And this gives us the other form of the double angle identity, 1 minus 2 sine squared x. I'm going to go the extra mile, solve for sine squared x, because that's what I'll be switching this out for. So it'll be sine squared x is equal to 1 minus cosine 2x over 2. Okay? So I can sub that out for 1 minus cosine 2x over 2, all squared dx. And then here I'm going to take out the 1/4 and distribute everything. So I'm going to get a 1, right? When I have 1 minus cosine 2x's, I'm going to get a 1 term. I'm going to get a minus 2 cosine 2x term plus cosine squared 2x dx. If you didn't follow that, make sure you can just FOIL it out on your own and make sure you can get the same thing. But the point is I can do this. This is a 1/4. So I can integrate this. I can integrate this. I don't know how to integrate that one, though. But it's easy. All you got to do is this whole procedure again. Except now we don't have to rederive the double angle formula for cosine squared. We just know it's going to be 1 plus cosine 2x over 2, just because of the symmetric nature of sines and cosines. So this is going to be 1/4 integral of 1 minus 2 cosine x plus, now instead of cosine squared 2x, I'm going to write 1 minus cosine 4x over 2. And it's a 4 because there's already a 2 in there. Okay, so when I multiply by 2, get a 4. So 1 plus cosine 4x over 2. And it's a plus because we're not actually solving for sine, we're solving for cosine squared 2x. If you wanted to, you could do the same procedure for cosine, and you would get that cosine squared x is 1 plus cosine 2x over 2. But I'm not going to do that just for the interest of time. Or you could just look up these formulas. You can do that too. So there we have it. Now that's an easily doable integral. We have 1, we have 2 cosine x, we have 1 plus cosine 4x over 2, all very easy terms. And that's basically the approach to use when you have sines and cosines inside an integral multiplied by one another, and you're trying to solve the integral. So there you have it.